In the beginning of the chapter itself, we learnt about advantages of AC over DC. The main advantage of AC was it can be transferred to a very long distance with the minimum power loss, and which is more economic than the DC. And one more thing is, this AC can also be converted from high value to low value, as well as it can be converted from low value to high value. But this is very difficult. The conversion from high to low value and low to high value is very difficult in the case of DC. That is why it is also an advantage of AC over DC. Then how to convert a high voltage of AC into a low voltage of AC? That can be done with the help of a device called transformer. I hope that you already know about the transformers. You might have seen this. When you are walking in the road, you may saw the electrical pillars. In some pillars, a big box is fixed, and that is actually transformer. So, which is used for power up the current or voltage. It will step up the current or voltage. And if you saw your mobile charger, it will has also a transformer, but it is in a smaller size. But what you observed in the road or in the electrical pillar was a bigger one. But still, they are the two transformers. But so there is a difference between these two transformers. Okay. So let's study what is the difference and what are the construction and how does it work. So let's see everything. So transformer means, I told you, it is a device which is used to convert the high voltage into low voltage and low voltage into high voltage. Yes, that's right. Transformer. The name itself indicates that transformer. It is transforming. It is changing something. It is a device which is used to convert high voltage to low voltage or low voltage to low voltage to high voltage. So this is the functioning of a transformer, and it is also definition of this transformer. Now let's see the structure of this transformer. So transformer consists of a core, a metallic structure. This is a metallic structure, and on which wires will be put. They will take the copper wire, and that copper wire will be wounded along these arms, or it can be called as the limbs. So there are two kinds of transformer, means where the wounding will be different. Then what is the difference between these two transformers? In this type of transformer, the wires are wounded on a single link. On this link, wires will be wounded. In this type of transformer, wires are separately wounded. Here, one wire will be wounded along this link, another wire will be wounded in on the another link. So that I told you, two wires should be moved on the links. So those wires are called as a primary and secondary. Okay, so the primary means the circuits, the wires which is wounded on one side, and all that circuit can be called as a primary circuit. This is the primary one, initially one. Primary circuit or primary turns. And secondary one is there. Another one kind of a wounding of turns are there, that is called secondary. In this also we can see primary here, which are separately wounded. This is the primary, this is the secondary. Secondary coils are also wounded on another link. But difference between this one, these coils are wounded separate on separate links. Here it is wounded on one another. So this is the main difference between these two transformers. So to explain this transformer, we have to make some assumption, or in other words, we have to take an ideal transformer. Then what is an ideal transformer? Why we should take? If you have taken ideal transformer, or ideal transformer means where resistance of the winding will be same. This is the one point. Second point, there will not be any flux leakage. There will not be no magnetic flux leakage. That is the second point. Third point is there will be no eddy currents. So I told you 3 points. The resistance of the windings will be 0. See, here we have wires and the resistance of these windings is equal to 0. So that current can easily flow. There will not be there will not be any loss of current or energy in the form of heat, because there is no resistance. That is why no power loss. And second one is there is no flux leakage. Flux means it is called magnetic flux. Then why do we come with the magnetic flux, concept of magnetic flux? Okay, so to understand that, we should know on what principle this transformer works. See, this transformer works on the principle of mutual induction. How? See, this is a primary coil. Through the primary coil, AC current will be passed. AC current is passed through this primary coil. AC current will be passed through this. As the AC current passes, it will induce a magnetic field. So that magnetic field will be linked with the secondary coil. Change in magnetic flux linked with the another coil, which will induce a current in the secondary coil. See, there is no contact between these two coils. They are insulated. Here also, these two wires are insulated, and the neighboring turns of a single wire also insulated. So there will be no contact between them. Still, current is produced in the secondary coil. This is because of change in magnetic flux produced by this coil is linking with the second coil. That is why it induces a current in the secondary coil. This is according to the Faraday's law of electromagnetic induction. Yes. So see, so the primary coil produces a magnetic flux, which should all link with the secondary coil. Sometimes what will happen is, some of the flux will not be linked by the second coil. It will be wasted. That will not connect or enter into the secondary coil, that will go away. That happens because of the poor design of this core or because of the material used. So in the ideal transformer, we assume that flux leakage is also zero. So if the flux is leakage, then the energy will be lost. So if we consider there is no flux leakage, then there will be no power loss. Then another concept is eddy currents. Eddy current means when a bulk piece of material, when a large piece of material is subjected to changing magnetic flux, an EMF will be induced, due to which current will flow. Again, that will heat it up, energy will be lost. And in the ideal transformer case, there is no eddy current or formation or creation of a eddy current in the body. So this is an assumption we have to make because to say that power loss is zero and to prove the relations or the mathematical equations. So this is the assumption we have to make because of that reason. Yeah. Now your primary coil is there, secondary coil is there, and this works on the principle of mutual induction. Now see here, the current will flow in the primary coil, it will induce as a magnetic flux, and that magnetic flux will be linked with the secondary coil, and also it will be linked with the primary coil because they wound on one coil. They are wound on a one system. That is why flux will be linked with the both primary and secondary. That is why an EMF will be generated in the second as well as an EMF will be generated in the first one. And the EMF generated in the first one can be called as a back EMF. That you already know it. This looks like a semiconductor, self-inductance coil. Okay, that is why an EMF induced in self-inductance coil is called as a back EMF. Now, back EMF is induced. Let's say supply voltage is VP. VP is a voltage. It is a supply to the primary end. Voltage that we can receive from the secondary coil can be written as a ES. Okay, and EMF induced due to the changing magnetic flux with this can be written as a ES. And the back EMF produced in the first primary coil can be called as a VP. So I have defined 4 terms there: VP, EP, ES, and ES. VP means it is a voltage supplied to this coil. EP means it is a vacuum induced EMF. ES means it is an induced EMF in the secondary coil. VS means it is a voltage developed across that terminal. Now from Faraday's law, what do we know that? Flux linked with each coil is same. That is E is equal to minus d phi b divided by d. And for if you have taken n number of turns, then how we have to write n into d phi by dt. So d phi by dt is a constant always. If you take how many number of turns, d phi by dt is a constant. But which is a varying there? N is a varying. That is why d phi by dt, magnetic flux per unit time, is same in all the terms of the two coils. Okay? Let's write from Faraday's law. Let's write EP. EP is equal to minus number of turns in the primary. Let's call it as INP into minus d phi b. Yeah, right. And from Faraday's law, this one. Also, we can write ES is equal to, ES can be written as minus N P have written So there you are trying ns, number of turns in secondary can be called as ns d by v divided by dt. Now, so what you can write is here EP you have written, ES also written. So let's write, we know that or you can write like this. If secondary coil is not connected to any circuit, okay, see here, the secondary circuit is not connected to any external circuit. So we are not connected any kind of a component over there. In other words, we are not connected any load to this end. Load means it is a one circuit or it is a resistor. We are not connected to anything over there. In that situation, from KVL, what you can write is, I am writing this as EP is equal to V. See, we imagine that resistance of the winding is equal to 0. Okay, so here we have connected one AC source. Let me write here. It is not visible here, that's why. See, here we have connected BP, this is EP, this is ES. Okay, so we have connected EP or BP here. Source we have supplied to the primary coil. So the resistance of these windings is 0. And if you look at this, it simply seems as inductor is connected to AC circuit. Yes. So in that case, if you apply a KVL to this loop, then what we will get is potential across this must be equal to the potential across this. That is what I have written. What I have written, EP is equal to VP. Potential across this must be potential across that. So because of this changing magnetic flux in the secondary coil, it produces EMF which is ES, and that ES must be equal to VS. Because this circuit is open now. That is why whatever the potential developed here, that must appear here. That is why ES is equal to VS. Yeah, that we have written from KVL, EP is equal to VP. Similarly, ES is equal to VS. So now we wrote ES is equal to VS as well as EP is equal to V. So from this, after writing this, what we can do is, we can write already we have written the equation for ES and EP. Hence, ES is equal to EP is equal to VP, which is equal to minus MP into d phi by dt. And similarly, ES is equal to VS. ES means you should write VS is equal to minus NS into d phi by dt. Now let us take this equation number 1. This is 1 divided by 2. Equation 1 divided by 2. Equation 1 divided by 2. VP by VS. VP by VS. 1 divided by 2, which is equal to minus NP by NS. Minus d phi by dt is there, and divided by minus Ni d phi by dt is there. d phi by dt cancels, minus d5 by dt minus d5 by dt cancels. So we left with so remaining are np by ns. So vp is equal to vp by vs is equal to np by ns. This is one relation. Then can we rearrange anything? Can we identify anything from this? Yes. Voltage across secondaries. Voltage across a secondary is C. Secondary you want to find out, Vs you want to find out. Vs equal to, take the Vs here, take the MP over here, Ns over here. So Ns by MP into V. Okay. Now see here. Now Vs is equal to Ns by Np into Vp. Or you can write another one also. Both are correct. Let me write voltage across primary. Let it be secondary. Primary. So Vs is equal to Ns by Np into Vp. Now see here. Here Vs is directly proportional to Ns and Vs is inversely proportional to N. Vp is a constant one because we are providing a one constant value potential level. So this Vs, variation of Vs depends upon this Ns and Np. Let's talk about this Ns. If this Ns is greater than Np, okay, I am repeating. If the Ns is greater than Np or Np is less than Ns, this value is less, this value is greater than this. So if Ns is greater than Np, number of turns in the secondary is greater than Np, then Vs is greater than V. Okay? Vs will be greater than Vp when Ns is greater than N. So then this Vs is greater than Vp, then the transformer can be called as a step-up transformer. Because output voltage, this can be output voltage, this can be called as input voltage. Output voltage is greater than the input voltage. That is why this kind of a transformer means where Ns is greater than Np. If Ns is greater than Np, then such arrangement is called step-up transfer. Step-up transform. Step transfer. If Ns is less than Np, then see here, Np is greater than Ns. I am telling in either way. You can say Ns is less than Np or Np is greater than Ns. In that case, Vs will be less than Vp. So output voltage is less than input voltage. Then this happens when Ns is less than Np. Then such arrangement is called as a step-down transformer. Then what is the meaning of this? Step-up transformer and a step-down transformer. Step-up transformer means if you have given a very low amount of voltage, if you have given some voltage to the input, you will get a high voltage at the output. That's why you are stepping up, step up, and that kind of a transformer is called as a step-up transformer. If the input voltage is high, output voltage is less, then such type of a transformer is called as a step-down transformer. So these are the two kinds of a transformers: step-up transformer and step-down transformer. Yes. Let me write here. if Ns is less than Np, then such arrangement is called step-down transform. Such arrangement is called as a step-down transform. And one more assumption we made, that is power loss is equal to 0. There is no power loss. That is why what we can say is input power must be equal to the output power. And if you take the sum of them, that should be equal to 0, because power loss is equal to 0, right? That is why we assumed that power loss is 0. We assume that power loss is 0. That is why input power, that is I can write, okay, that is input power is equal to output power. Input power is equal to output power. Input power can be written as input power, that is input power, voltage is a Vp, current is Ip. It is equal to Vs Is. If you rearrange this, take the Vp here. So Vs by Vp here, Vs by Vp is equal to Ip by Vs. This is another relation. We can write this as 2. In previous to this, we have written Vs by Vp is equal to Ns by Np. So take it as a 1. Take that as a 1. From 1 and 2. From 1 and 2, Vs by Vp is equal to Ns by Np, which is equal to Vs by Vp means Ip divided by Is. So this is a relation we obtained from this derivation. So this is a relation, you can see the relation between number of turns and voltages, as well as you can see the relation between the current and number of turns. So this is helpful for the practical purposes or for the calculation purposes. So this is about the transformer, and there is some power loss. We told you that this transformer has an ideal one. Ideal means we have assumed the three concepts. That is, first one is a magnetic flux through the coil is leakage of magnetic flux through the coil is 0, and another one we take a resistance of the winding is 0, and eddy currents produced in the core is 0. Actually, these kind of transformer, what we assumed the transformer as an ideal one, which in reality doesn't exist. So that is why what I told you, some of the assumptions we made, that are the energy losses in the case of, or the power losses in the case of a transformer. So this is about the concept of this transformer.